I'm a smarty who remembers things. Sometimes. Today we are going to introduce one more force, and based on what I'm seeing from my 3 o'clock section, I do not want to also introduce springs after all. Friction has 2 pieces to it, so I think we're going to keep it to friction today. At least. Okay, so here is new information. This is maybe, depending on how you all do today, this may be the last new information that you need before the midterm. Let's see how things go. I want to introduce to you a new force, the force of friction, surface friction. Please remember that drag, this being era freaking zona, is too conservative for me to teach you about drag. So we are not dealing with drag in here. You can blame the Arizona Board of Regents on it. Just kidding. Not dealing with drag because its equations are god-awful, and you don't want to go there. Ain't nobody got time for drag. We're going to deal with surface friction only. 2 solid surfaces scraping, skidding, sliding, sticking against each other. So surface friction. Let me write this down. Friction, not drag. Friction. Okay, so the first thing you need to know about friction is that there are 2 kinds of friction, actually. Frick and fuss. FK is called the K stands for kinetic. I can remember things. Kinetic friction. Leave a little space if you're writing this in your notes. There are words that I'm going to put under each. Static friction. What do you know that uses the kina prefix? What's kina about? What is kinematics all about? Movement. That's right. Kina is Greek for, I'm butchering it, I don't know Greek, but kina is the Greek prefix for the Greek word for motion or something. Kinesis, I think. Whatever. Think of, to remember this, think of the cinema. Cine, kina, same root word. Kinematics, study of motion, science of motion. Kinetic, the kind of friction that involves moving. Static, what is stasis? What does it mean to be in stasis? Frozen, stuck. Static, not moving. Static electricity is electricity that does not flow till it zaps you. It's sitting there. Now, there's an important distinction here. There's an important confusion here. There's an important conceptual potential misconception here. Between objects. So, for instance, I'm exerting friction forces on my iPhone right now. I'm moving the sucker around, yeah? Is it moving? Is it in motion? Obviously, yeah, you see it moving around. There is a friction force between hand and phone. I ask you this, is my hand moving in the same way that the phone is moving? Is the phone slipping or sliding or skidding over my hand? Is this motion or no motion between the 2 surfaces? No motion. This is static friction as the 2 surfaces are moving over each other. My feet on the floor, I am walking along. Am I skidding? Am I moonwalking? Am I sliding? No. Normal walking. This is static friction. Your car driving along normally on the road. Are you leaving tire skid marks? Is that static or is that kinetic? Static. There is no sliding. The surface of the wheel is at rest. The bottom surface of the wheel rolling over top of the pavement is not skidding along the surface. It's rolling on top of. So all of those are examples of static friction. You want to see kinetic friction. Oh, okay, there we go, doing the Kramer. You guys know that reference? Okay. Don't blame me, I'm 41 years old and I don't want to break a hip. So that's a kinetic friction. If there's skidding, if there's sliding, if there's slipping between these surfaces. For instance, if I don't want to do this with my phone. If I take my purse and I really whip my hand out of there was static friction. Whoa, that was a tension. There was static friction between my hand and the purse. Notice, by the way, notice which way the purse goes. I'm going to yank my hand to your left. Which way did the purse get pushed? To the left, right? To your left. So I exerted a leftward static friction force, kinetic friction force on it. That kinetic friction force is actually what moved the bag. It is a common misconception to think that friction always opposes motion. No, 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 no. Friction, both kinetic and static, opposes relative motion. If my hand is going to your left, sliding underneath the bag, sliding from the bag's right to its left, the static friction force it's going to exert on the bag is to the left. It's going to push along. The friction force of the bag on the hand is backwards to the right. In each case, the static friction is opposing the relative sliding. It's trying to stop those surfaces from slipping in that direction, yeah? So if I pull, you guys know the trick where you take a tablecloth and yank it underneath the plates? Suppose I have a tablecloth and I yank it hard underneath the plates and I yank it to the right. Google question, let's see everyone's views. Question J, which direction is the friction force of the tablecloth on, hold on Gina, let me ask this. If I forget, ask me again. Let me ask this. What is the direction of the force of the tablecloth on the plates if I pull the tablecloth off rightward? Think that friction is to the right or to the left, or not at all? Okie dokie. Seems like it's about evenly split. On average, y'all are not sure. On average. Okay, so here, let me reason about it this way. Let me encourage you to think about it this way and maybe change your answer. If when I pull the tablecloth out from underneath the wallet, in this case, the table, here's my tablecloth, here's my plate. When I pull it out, if the wallet does not slip over top, if the table cloth does not slip under, which direction will the glass go? Yes. Yes, sure. Let's go down. Think about directions here. Here's a tabletop. Here's a sheet. Oh, I don't want to draw myself. I'm just going to say here's the tablecloth. I want to draw a hand pulling it. And here is a plate. The tablecloth is going to get pulled hard to the right. And I said what I was going to say a second ago wrong, by the way. Thank you for making me do this so that I read it carefully. pulled rightward. Our goal is to find the direction of friction on the plate here. And I want to challenge you to ask, think about it this way. Which side of the tablecloth is the plate coming out from under? If I pull the tablecloth rightward, which side of the tablecloth does the plate come out from under? So think about this one. This is not a Google form. Item one to think about. Which side of the cloth? The plate slip out from under. Wait, slip over. If friction opposes that motion, okay, and why don't you change Google Form J? You can edit response, J, submit. And if you change your mind, consider this, which side does it slip out? And then if friction is opposing that, question? Yeah, yeah, sure. Yeah, because I hide all the ones before J when I'm looking at these. Yay, good. That helped. You think about that correctly. On average, lots of people now see correcto mundo. This is J for Juliet. Okay, let's try the experiment because we're not at everyone agreeing here. Let's try the experiment. I have aligned my wallet, here's our plate, with the edge of the table here. Yeah, you see that the edge of the wallet is on the edge of the table? I'm going to yank the tablecloth out to the right, the paper out to the right. If friction pulls it rightward, the wallet will fall off the table. If friction exerts a leftward force on the wallet, it'll recoil back onto the table further. Yeah? You agree? Let's try the experiment. Ah, that was too fast. There is a recoil there, but you couldn't see it. Which direction did the right? That's correct. If the tablecloth sliding out from under the plate, there is relative motion this direction, then friction wants to oppose that by pushing this way. The table cloth pulls the plate on underneath it. Let me ask then this question, think about this. What force is opposing the rightward motion of the plate? What force is opposing that rightward motion? Yeah. What force opposes that? I mean, it's moving, right? I'm moving it to the right. What opposes that motion? Tell me in K, what force pushes it left? What do you think? I'll remind you that weight, gravity, does not point left, right. If I jump up, gravity does not accelerate me that way. So weight is not correct. Weight does not act horizontally. This is question K, K for kilowatt, kilo, Kendra. So again, what force, my question for K, is what is opposing the motion of the wallet there? What is acting back leftward? What is pushing backwards on the wallet? We discovered just now that friction acts to the right, moves it to the right. What force opposes that? Okay, I've got a lot of people telling me normal force. I will remind you that normal force acts perpendicular to the table. Horizontal table, vertical normal force. Normal force pushes up. And again, a fair number of people told me gravity, wait, Earth doesn't pull you sideways, Earth pulls you straight down. Weight force does not act left-right. The correct answer is there is no leftward force on the wallet. The wallet interacts with one object underneath it. The object interacts with the tablecloth. I'm just going to say wallet and paper. The wallet interacts with paper. I'm confusing myself. Wallet interacts with the paper. It is touching. There's nothing else touching it. There's nothing else to act on it to pull it left. And friction can't pull it both right and left. A force is either right or it's left. It can't be both at the same time. The correct answer is there is no other force opposing it to the left. No force. A couple of you said that. Good. Okay. Now, last, let me ask about friction of a cardboard box in the back of a truck. I get in a truck. I zoom forward. Let me draw it. Here is a truck. Oh, for goodness sake, that's too artistic for you guys. You shouldn't see that or you'll feel bad about your own art skills. Is that a truck? Is that legible as a truck? Can you guys? The what? The carbonator? You mean the cardboard box? Wait, box. Okay, so I'm going to say there's a truck driving over a, what should I call this? A road. Truck driving over a road. And there's a box on top of the truck. And the truck accelerates hard to the right. Right? The truck is going to gun it to the right. Wait, sorry, hold on, wait. There was a cowboy that asked a question in the chat. How can an object have both static and kinetic friction? Gina asked, how can an object have both static and kinetic? It can't both at the same time from a given object. Either something is slipping over something or it's not slipping over something. However, you could have two objects exerting a force at the same time. So for instance, if I pull this wallet over the tabletop with the paper, the paper is touching two things. The paper is touching tabletop. There's relative motion there. The table is touching paper. Paper is touching tabletop, so there's a kinetic friction there. The paper is also touching the wallet, and they're not. I'm not pulling fast enough for it to slip out under, so that's a static friction there. So there can be two different kinds of friction if there are two different objects interacting. Hold on, Gina said, but a follow-up to that is, you said what? Please carry on. I want to hear your question. Anyone else remember me saying something that sounded like kinetic and friction at the same time? Okay, please do type, Gina. I want to hear that, but I will do my darndest to remember to look at this in 2 minutes. Okay, so identifying static versus kinetic, muy importante. Identifying the direction of friction, muy importante. I want you to think about this. Riddle me this, Batman. A truck gun. Oh, okay, she typed faster than I thought. Let's ask it. There we go. You said the object had static kinetic friction. Did I? Do I have static kinetic friction? I said there are two kinds of friction that a surface can exert. Static friction, kinetic friction. Either one or the other at any given time. This, for instance, if I pull this slowly, the paper is pulling static friction on the wallet. They're not sliding over each other. If I pull this fast enough, the paper is moving under the wallet, sliding. The wallet is sliding backwards over the paper. So that was a kinetic example. They can both happen, but not at the same time. I'm not sure what words I said that sounded like this, though. I'm not sure if this answers your question. Please continue to ask. I am going to go on to the next example while you type, if you type. Okay, so truck drives, cardboard box is not secured, is not belted down, and there's some possibility of slidage going on. I challenge you to tell me this. The car guns it underneath the box. Which direction does friction push on the box? Right or left? Google Questionnaire, let me see what y'all think. Everyone thinks. Which direction does the box feel a force? The truck guns it hard to the right. Vroom, vroom. The truck is accelerating this way. This way. It is not turning that way. It is accelerating this way to your right. No, you don't. You don't go backwards. You don't go backwards. The bus goes forward around you. You stay where you are. I had wrong answers, and now some of them are turning correct. Okay, let me apply the same principle here that I said before. Which direction is the box moving relative to the truck? Is the box going to hit the cab of the truck, or is the box going to hit the tailgate of the truck? Okay, if friction opposes that motion, you may change your answer. If friction opposes hitting the tailgate, which direction does friction act on the box? Google question now. Think about this. Again, here's how to reason about this. The truck guns it underneath the box. I mean, the box is going to hit the tailgate, right? Yeah. The box doesn't jump forward to hit the box doesn't jump forward to hit the cab. Not until you brake. The box experiences a relative motion hitting the tailgate of the truck. Which direction is friction going if friction opposes that relative motion? Incidentally, this is exactly the same as what I just did with the wallet and the paper over there. This is exactly the same. I'm pulling one object out from under another object. The correct answer is exactly the same as before. It is to the right. Fricted force acts to the right. Turn to each other and discuss this. Turn to each other and discuss this. Friction is what's making the box move forward. In this example, the truck is just moving forward faster than the box will. Again, discuss this idea. Friction is actually what's making the box move. It hits the tailgate of the truck because the truck is just accelerating around it faster than the box can. Turn to each other and discuss. Yeah. Yep. Yep. Yeah. Yes. Friction opposes the fact that the box smacks into the tailgate. Friction opposes the relative motion between the two surfaces. Wait, from your perspective, yeah. Truck is moving underneath, the tailgate smacks into the box. Friction doesn't want that to happen. Friction is opposing that direction of slippage. What direction is friction acting if it's pushing against the backwards? The relative backwards. The box actually recoils forwards. The tailgate hits the box because the truck goes faster than the box is. Yes, exactly. Well, there's a friction in either case. The truck accelerating not crazy fast, or if it's belted down, whatever. If you're not gunning it so fast, then what is causing the box to move along with the truck? It's a friction force, static in that case. Question. With no friction, the box can't move along with the truck until it smacks into the tailgate, and then the tailgate would exert a normal. But with no friction, the truck can't go anywhere. Remember, it's friction that makes in the truck bed. If I have a totally frictionless truck bed, the box won't go anywhere. The box will stay exactly where it is until the back of the tailgate hits it. Half a sec. Say again? Okay, go for it. Mm-hmm. Yes, not just moving, accelerating. Because the force that you applied was to the box in that Desmos whatever example, right? But what is pushing on the box in this example? You're not applying a force to the box. The truck is gunning itself around the box. Movement is not a force. Friction is a force. If there's no friction, there's nothing to keep it moving along with. Good, good. Other questions? Really good pair of questions. Okay, so correcto answer here is the box is actually accelerating to the right, just not accelerating as much as the truck is accelerating around it. Okay, I think that is enough about the identifying. Wait, one more. Which direction is the friction? M, which direction is the friction of the road on the truck? Which direction is the friction of the road on the truck? And N, what kind of friction is this? So Google question M, which way does road exert friction on truck? Friction on T. Question N, what kind of friction is it?
I said that last time. I would say it was. Oh, yeah. No, yeah. Well, let's think about. Oh, no, Marcus spelled it. It's the wheel.
Check your notes, by the way. For N, I already told you the answer earlier when I was introducing kinetic and static. Also, this is M and N, not O. Ooh, okay. Very few are getting M. Riddle me this, Batman. Riddle me this. If the truck has an icy surface underneath it that you butter the icy surface, if you took away any friction of the road, can the car go anywhere at all? It spins its wheels, vroom, vroom, complete icy surface underneath. Is it possible that the truck moves at all? Even a little bit? No, no, no. If you have a completely icy surface, you vroom, 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 the wheels spin in place. It is friction that lets you walk, drive, whatever. Friction does not always oppose motion. Friction opposes the relative motion. Here's how I walk. I push my leg backwards. I push my leg backwards. I push the ground backwards, and by Newton's third law, the ground pushes me forwards. That's what happens when you take a step forward. I am moving my leg backwards. Look at where my leg goes. Now it's level with my body. Now it's behind my body. I am pushing my leg backwards. The ground is pushed backwards, pushes me forwards. The ground pushes me forwards. So if there is no friction, this truck ain't going nowhere. You ain't got no traction, you're not going anywhere. You stand on perfectly slick, icy lake on skis or whatever. Are you going anywhere? You can go like that. There's roller skates on top of an icy lake. You could do whatever you want. You're not going anywhere. It's going to be moonwalking in place. So let me ask this. If it is friction that makes the car vroom, makes the car go somewhere, and the car is accelerating to the right, which direction must friction point? There is only one horizontal force acting on the truck. The truck accelerates rightward. Which direction must the net force on the truck be? Okay, hold on. Google question O. The truck accelerates right. Which direction is net force? Let me see this. The truck accelerates to the right. Which direction must the net force be? You are encouraged to look at Newton's second law for a second. For a second. The second for a second. An object with a positive A has to have a positive F. Correct answer is right for O. If the truck accelerates right, then the net force is to the right. Google question P, what force in this example is providing the net force? What is the net force coming from? What kind of force is this in this example? What is making the net force? Net just means add all of the forces together. Net means total. What is the nature of this rightward force? Is it a tension, a normal, a weight, a friction, a spring? Acceleration is the result. Acceleration is not a force. The kinds of forces from your dictionary: normal, weight, tension, spring, friction. And it's not spring because we haven't covered that yet. So what is the force which makes the net force? What is the horizontal force on the truck that I said a few minutes ago? Okay, here's how to rule out, half a second. Here's how to rule out wrong answers. Normal means right angles. If you've got a horizontal surface, what's at right angles to horizontal? Normal force acts up. Which direction does gravity pull? That normal and weight are not responsible for the truck accelerating. If you were in deep space, if you took away the weight force, yeah, things would be different. But it's not weight that moves you right. Okay, what I just said before, walking you through how to think about this, is if you took away any possibility of friction under the car's tires, it ain't going nowhere. So what's the nature of the force that allows the truck to move? It's friction. Friction is traction. Friction is the car pushing on the road pushing on the car. That's what makes things move. Trucks, anyway, cars, feet. Write that down. Write that down. Without friction, you couldn't move anywhere. You'd just be moonwalking in place. So net force is to the right because the acceleration is to the right. The net force comes from the friction force. Google question Q, which direction does friction act? Put the puzzle pieces together. I'm leading you right up to the lake. All you got to do is drink. My horsies, my little ponies. James. P was what forms the net force. Which force or forces, it's a force, is making net up? Up? No. Okay, big fat hint for Q for y'alls. Which way does the road friction on the truck? Question me. Let me be precise. Of road on truck. Which way, left or right, is the friction force that the road exerts on truck? Okay. The correct answer is to the right. A is right, so F net is right, and F net is friction, so friction is right. The moral of my story here that I've given three different examples for to illustrate, think about the commonalities of these examples. Friction doesn't always oppose motion. Friction opposes the relative motion. If the tire pushes the ground backwards, think if the tire were on, a rug, wouldn't the rug be spat out the back as the tire spins, right? The tire, just like my leg, I move my leg backwards relative to my body. My leg pushes the ground backwards. Newton's third law says the ground pushes me forwards. Friction opposes the relative motion. To figure out whether the friction is slowing down or speeding up the object, you've got to use reasoning. It is not always a simple rule that friction is slowing things down. Yeah. Correct. If the friction is what's accelerating the truck, then absolutely. Now, if the truck is braking, then it would be opposite. I mean, friction is what allows you to start moving. Friction is also what allows you to stop moving. Friction is the force that allows us to go and stop going when we're walking or driving around. Friction is a versatile force that could do lots of different things. You have to consider in any given example, in any given case, what is this object doing to that object? The road is what is pushing on the car. The road is the external object exerting the onward force to get the car moving. Which direction does the car move? Car is accelerating rightward. Friction is rightward. If the car is going rightward and skidding to a stop, braking to a halt, the road is pushing leftward on the truck. Okay, so we can hopefully identify the kinds of friction, static and kinetic. That was getting better. The direction is a little bit harder, but we could practice that more. Let's do now the equation for kinetic friction. Here we go. Go back up to your main notes, not the examples. Hopefully you left some room. If you didn't leave some room, just put a box in. Muy importante. This is the Greek letter mu. It's written like a U with a long tail on the left. If you're typing it into the Google form, you could say MU, or you could just use the letter U. This is how the Greeks write M, the M sound. What is what capitalized? I use lowercase f's to distinguish. I like to use capital F for an arbitrary force or net force. Friction force. I should be precise. The kinetic friction force. This is called the coefficient of kinetic friction. And this is the normal force that the same object is exerting on whatever is getting the friction. Kinetic friction's easy, equation-wise. If you could find the normal force on that object, you can find the kinetic friction force. Mu, where does mu come from? Other than a kitten, mu is given. Mu is tabulated. Mu is just a number you look up. I will give you mu, or I will give you everything but mu and ask you to find mu. It's just a number. The number depends on the surfaces. Example, asphalt on rubber, mu equals 0.8. Kinetic mu equals 0.8. Ice on ice, mu equals 0.05. Steel on ice, mu equals 0.1. It's just a number. Coefficient of kinetic friction. Now, there is also a coefficient of static friction, but But, and this is a big but, that mu s times n is not how much static friction there is in any given situation. There is something tabulated, mu s, coefficient of static friction. You can look it up, and it does not tell you, mu s times normal does not tell you, not equal to tell you what the static friction force is at any given time. Mu Sn tells you the breaking point. The limit, the max value of static friction. It is a muy common goof for people to be given a static friction coefficient and jump to static friction equals mu Sn. No. Static friction, mu Sn is the maximum value you can get. Static friction can apply less. Static friction can apply 0. Static friction can apply that value. If you try to get static friction to exceed mu Sn, then slippage happens. Static friction, mu Sn, the mu Sn equation, is the maximum value. It is the stickiness of the surfaces. Once you exceed that static friction, or if you try to exceed that static friction, then you are in motion and static friction no longer applies. I want to emphasize this. Let me do an example. Follow along carefully. Look carefully. Right now, there are no horizontal forces applied to my cell phone. What is static friction providing right now? Is static friction acting on the phone? No. Static friction exerts 0 newtons. If static friction were exerting any force whatsoever, the phone would have to accelerate, because I just told you there's no other horizontal forces, right? This phone is not accelerating. Therefore, horizontal force, actually all directions force, must be 0. Okay, I'm going to apply 0.1 newtons to this phone with my finger. 0.1 newtons. Is the phone moving? Is the phone moving? No. If I am applying 0.1 newtons and the phone is not moving, what static friction must be providing? Oh, that's too quiet. Google question R. If I am applying 0.1 newtons to the friction, 0.1 newtons to the phone, and the phone is not moving, what can we deduce about the static friction force? Phone is not moving. What is the value of static friction if I apply, this is question R, by the way. Ooh, you guys are not getting this point. Okay, hold on. No one's getting this. If the phone is not moving, Google question S, here's how to reason through this. Here's how to think about this. Google question S. The phone is not moving. What is his net force? What is the net force on this phone if I apply 0.1 newtons to this and it's not going anywhere? What is the net force on that phone? Google question S. I am applying 0.1 newtons. It is not going nowhere. If there were a net force on it, F equals ma says it would have to accelerate. Most of you all are concluding that there is no net force. Again, if there is a net force, no matter how small, things must accelerate. If he is not accelerating, there can be no net force. If there's no net force, and I'm applying 0.1 newtons, There's no total, there's no net. If I add together everything, it balances to 0. If I apply 0.1 newtons, what's the static friction force? Try this again. Question T. What is the value of the static friction force if it is not moving and the total adds up to 0? Think carefully. I push it with 0.1 newtons. The total is 0. What must static friction be providing at that moment? T, T, T. Better. About half of you. Okay, so hold on. Total force means add together all the forces. If I push force equals 0.1 newtons, and I don't know static friction force, but I do know that total force equals 0. The meaning of total, again, F net equals I applied 0.1 newtons forward. It's silly to write down one number and the rest not. And there's static friction backwards. Can you solve this equation for static friction? Google question U, solve this equation for static friction. There's nothing in total. I'm pushing with 0.1. How much must static friction provide? Use the equation, Luke. That's more like it. This is U. 1, where's 1 coming from? Okay, the value of static friction, let's plug in and solve this equation. 0 equals 0.1 minus unknown. The unknown value is 0.1. Static friction is 0.1 in this case. I'm now going to apply 0.5 newtons. Is the phone accelerating? What is the net force on the phone? Google question R, V, what is the value of static friction now? I apply 0.5 newtons. The phone ain't going nowhere. Can you deduce what static friction is? I apply 0.5 newtons. The phone ain't going nowhere. Yes, that's my whole point for leading this through this, is to understand how do you get static friction. You can't just use μSn. No. Wait, you mean it's trial and error for us? Yes. What we would have to do to find, if we didn't know μs, this is how you would find μs. You would apply bigger and bigger and bigger forces till you find the breaking point that would allow you to deduce μs. Yeah, but first I've got to get everyone to understand, or most people to understand, that static friction is not equal to a set number. Okay, let's see how you got going. That's more like it. Most people have concluded that if there is no net force and I am pushing with 0.5 newtons, the only solution to the equation 0.5 minus something equals 0 is Fs must be 0.5 newtons. Okay, So consider this. Right now, static friction is providing 0 newtons. Right now, static friction is providing 0.1 newtons. Right now, static friction is 0.5 newtons. Is there an equation for static friction that is always true? Can I just find the value of static friction from a single equation? No, static friction is not a single number here. Static friction is not something you can plug into an equation. You have to use reasoning from the fact, wait, he's accelerating or he's not accelerating. He's accelerating at 1 meter per second squared and staying on the truck bed. How much must static be providing at this time? Well, plug and chug. Hell, let's do that. Let's do that. Let's do the truck example, but this time no slippage. 100 kilo crate. Whoa, that's huge. 10 kilo crate. Did I say crate? I said box before, didn't I? Okay, there's a 10 kilogram box on the back of the truck bed. Wow, that truck tailgate is big. No, I'm going to change this. Sorry. This is going to be 20 kilos, just for the sake of things. And why not? Let's make the truck 10,000 kilograms. And I'll give you the static friction coefficient between the road and the truck is 1.0. Okay, here's some extra information. Merry Christmas. The truck is accelerating at 7 meters per second squared, and I'm going to give you the additional information that this time, the, oh crap, does this work? Hold on, I have to do this in my head. Yeah, this works. Hold on, do it fast, do it fast. Yeah, this works, good. I don't like to give students unsolvable or incorrect problems. Okay, so my challenge question for you is, the truck is accelerating along at 7 meters per second squared, and I'm gonna tell you that this time the box is not slipping or sliding relative to the truck bed. It is being moved along perfectly well with the truck. Can you tell me, Google question, what are we on? W? W, what is the static friction on the box? Find static friction of truck on box. Hint, 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 hint. Everything we've been doing has been leading up to this point. Reflect on what we just did and what I've just told you in your notes. Yeah. Static friction is always going to be, well, okay. So static friction is what I've been writing down is the magnitude. You always have to discover the direction of static friction based on reasoning. Is this accelerating the box to the right? Positive number. Is this accelerating the box to the left? Negative number. Is this breaking the box from initial motion? Yada, yada. Any force can be positive or negative, but the equation that I wrote down is just the magnitude. Hmm. Mu is not the friction force.
You're right. Okay, keep the writer.
Look at what we were just doing, talking about how there is no single equation you have to use reasoning about what's going on. Again, I'm asking you about the static friction force on the box, given what is written on the board and the knowledge that the box is moving along with the car. Wait, did I do this wrong? Okay, hint time. Hint time. You cannot just plug in mu_sn. What does mu_sn tell us? It does not tell us the value of friction, static friction. It tells us the maximum possible value of static friction. Point dose. Static friction is the only reason this box is accelerating. Static friction is the only reason this box is accelerating. Static friction is what is pushing this box to the right to accelerate along with the car. Right? Static friction is the net force accelerating the box. Point trace, I told you the mass of the box and the acceleration of the box. Okay, think about those puzzle pieces. Google question W, you may change your result, change your answer. Tell me the static friction that must be happening to the box. Okay, let's talk about this. Still only a third of you getting at this point. What provides the net force? What did we just say provides for the net force? Static friction. Static friction is what is providing the net force. Do you know the mass of the box? Do you know the acceleration of the box? What does Newton's second law say about what force is required to accelerate a given mass at a given acceleration? One last chance to put the puzzle pieces together on your own. I will tell you that you're not going to guess physics. You have to reason about it. You have to actually engage with this sucker. If the box is sticking with the truck, if the box is not moving relative to the truck, then the box had better darn well be accelerating at 7 meters per second squared. It's not moving relative to the truck. It is staying with the truck. So whatever the truck does, the box does. If the box has no acceleration, then the truck is just going to leave it behind and truck drives by. Did you say? Okay, let's see if we got any more correct answers here. Okay. Meters per second. This is not a speed. Okay, the correct answer is 140 newtons. If static friction is net force and net force is ma, then static friction here we can only find with ma. Very last question, what's the max force that static friction can possibly provide? Yes. Okay, you know what F equals ma, yeah? Yeah, so what is the net force equal to in this case? You got a 20 kilogram box, right? What's its mass? Yeah, right. What's its acceleration? So what must the net force on it be? Okay, now if you've got 140 newtons of net force, and what is causing that net force? What is adding up to make net? What is propelling it forward? What kind of force? You're right, it's the truck is exerting the force, but what kind of force is this that's accelerating it along? Static what? Exactly. Static friction is the net force. Or is there anything pushing leftward on this? No, there's nothing else touching it. Earth acts down. Okay. So what can you conclude about the relationship between net force and friction force? So static is 140. The last question, one more time. The last question is, what is the maximum force that static friction could provide? What is the maximum possible force in this example? This is question X that you could possibly get out of static friction before the box starts to slide. Ultimately, what this relates to is how hard can you gun your truck's engine and have the thing not start to slide? How much, what is the maximum value of static friction? That is for you to decide. That's what I'm asking. One more time, I'm asking you, and then you may go in 2 seconds if you could tell me how much can static friction possibly provide here? I have already told you the equation to use here. There's the maximum possible value of static friction. Read your notes. Take a look back in your notes. MUSN tells you, what does it tell you? It doesn't tell you necessarily the current value of static friction. What it tells you is at the maximum value of static friction. So how do we calculate the max value of static friction? Multiply MUS times N, 156 odd newtons. Okay, we are out of time. We will finish this on Wednesday.